Share screen. We got this thing. Now we got to
View and then button.
view. Enter full screen. And this thing here, we're going to
Oh, yes.
hide,
One more.
hide that. And we'll put the people over on the side.
Okay.
If you, okay, Garam, I can see you. Others, if you want to ask a question or stop something, you can either raise your hand or get back on video and start jumping up and down and doing something. All right. So this is a talk. This is kind of a wandering talk with some very basic stuff in it, and some and then some discussion about things that have recently come to interest me, and I've tried to structure this so that you don't need to know too much about joint semilattices to get involved. So we start. I'm going to present some basic facts, highlighting some what I think are some landmark results with an ace of spades. I'm going to begin at the very beginning, but eventually I'll describe some unsolved problems that have captured my attention, and I will sketch the present state of knowledge on these. Actually, I won't be able to sketch the present state of knowledge on these because I got an email this morning from Drew, which changed the present, which may well have changed the present state of knowledge on these. So we'll mention that. Yeah, one problem concerns what are called conjunctive joint semilattices. These are joint semilattices in which the maximal ideals are abundant. And I worked on these a lot with Chip and Tega at LSU, and we wrote a paper about these things. And while we were working on those, a problem came up that we found we couldn't solve, and I announced it a year ago at the blast meeting, and a couple months later, Marcus Tressel wrote to me that he had solved the problem for distributive lattices, but not for joint semilattices in general. And so we'll talk about some tools that might help to generalize this. And that will be the first problem. The second problem concerns the duality theory due to Hoffman, Mislov, and Stralka between the category of discrete joint semilattices and the category of compact zero-dimensional joint semilattices and continuous joint semilattice morphisms. So we were looking at this last year. Jimmy Lawson suggested that it might be possible to extend this duality to encompass locally compact zero-dimensional joint semilattices. And he proved a lemma that could play a key role in achieving this. But that is not so easy as we imagined it might have been. So this is still very much up in the air. But nonetheless, Jimmy Lawson's lemma is really elegant. It's the paw of the lion, if you remember the story about Newton. You know the story about Newton? Yeah. The paw of the lion? Well, the story of Newton was that somebody circulated a difficult problem on brachistochrome or something like that, and challenged the public. Bernoulli did, okay. And Newton worked on it all night long and solved the problem and published the result. And Bernoulli said, you can recognize the lion by his paw when he read the solution. Okay. So we're going to begin with some basic definitions, which I'm sure you know, but it's always good to review definitions at the beginning so we have the same ideas in mind. A joint semilattice is a set L equipped with an operation V that is associative, commutative, and idempotent, and has an identity. So we'll always assume an identity. Smallest element, 0. A joint semilattice morphism is a function between joint semilattices that preserves 0 and the sup operation. We're going to call the category of joint semilattices and joint semilattice maps JSL. All right, L is a JSL to mean that L is a JSL object. Throughout this talk, I've put a few comments or theorems or remarks into gray. These are things that are not important for the main flow of the talk, but they're there to refer to if convenient or needed. A lattice, of course, is a joint semilattice with an additional operation, which is also associative, commutative, and idempotent, and what's called the absorption law that links the two operations together. Okay, more definitions. We have a number of different little constructions that are performed all the time when dealing with partially ordered sets or with joint semilattices. First of all, every joint semilattice is a partially ordered set where I define X to be less than or equal to Y if X sup Y is equal to Y. If X is a post set, X op denotes the same set with the opposite order. If Y is a subset of a post set X, then up Y is the set of all elements of X that exceed an element of Y, and down Y is defined similarly. We call Y an upset if it contains everything, if it's equal to its upset. That is, if it contains every element which is larger than any element in it. And similarly, we define downsets that way. Up X and up Y are defined to be the upset and downset of singletons. Okay. We note that the unions and intersections of upsets are upsets. Thus, the set of all upsets of a post set is a completely distributive lattice. Similarly, unions and intersections of downsets are downsets. So the set of all downsets is also a completely distributive lattice. If X is a subset of a post set, if X is a post set and Y is a subset, then we say that Y is directed if any pair of elements of Y have an upper bound in Y, and it's filtered if every pair of elements in Y have a lower bound in Y. A non-empty directed downset is called an ideal, and a non-empty filtered upset is called a filter. If X is a disjoint union of an ideal and a filter F, then I and F are both said to be prime. So the prime ideals in lattices, or distributive lattices in particular, play an important role. As we can see here, we can generalize this definition to an arbitrary post set, and in particular generalize it. We can generalize the idea of a prime ideal to an arbitrary post set, and in particular, we can generalize it to joint semilattices, but we will see later that the prime ideals play a role in the theory of joint semilattices, which is rather different from the role that they play in distributive lattices. By the way, all right, if L is a joint semilattice, then a subset is an ideal if it's a non-empty downset that is sup closed. That's the easiest way to think about what these things are. Now, this is a very basic result. There's a lot of notation on this slide, but basically this result is saying that every joint semilattice is a joint semilattice of subsets of a set. That is, every joint semilattice embeds into the power set of into the power set of some set. We say this with a lot of decoration here because the ways that this theorem is used depend on putting it into the setting in the right fashion. But basically what we're saying is that if we take the collection of all right, the mapping up arrow that goes from L, the mapping up arrow goes from L to UL, but it's not order preserving. It becomes order preserving if we take the opposite of UL. Now, the opposite of UL is also isomorphic to DL. We'll get to that in a moment. But we'll just run through this. We want to show here that we have a joint semilattice embedding of L into the opposite of UL. The opposite of UL is a lattice of sets. So the upset of 0 is, of course, all of L. And the upset of a supremum is the intersection of the upsets of each of the elements of the supremum. To see that this is an injective mapping, we notice that the upset of A is equal to the upset of B if and only if B is in the upset of A and A is in the upset of B, in which case A is less than B and B is less than A, so that A is equal to B. The attraction of this is that in group theory, one of the first things that you learn is that every group is a group of permutations of is isomorphic to a group of permutations of a set. Not the group of all permutations, but the group of some permutations of some set. So this is very much in that flavor. I think it's a well-known result, but I don't know that people have often compared it to Cayley's theorem.
Sorry, James. Do you have a good reference to who made this observation originally in some old paper? Like, is it dedicated?
Probably. I don't know. I have no idea. I don't know who first observed this. Yeah. Well, an interesting thing about joint semilattices is that studied by name, or they weren't studied. There was no focus on them as an object of mathematical study until about 1940. And Birkhoff looked at them, and also there was a German mathematician that wrote a monograph on Halbverbände in 1939. I forget what his name was, but I can get that to you. The first appearance of Klein-Barman, yeah. The first appearance of the word semilattice that you can find in the literature that's known to Google and is that some shoes that were advertised in the 1920 Good Housekeeping magazine were claimed to have a semilattice front. All right. So we're still working on very basic stuff. And this slide is got a lot of very shallow information in it. The main idea is that for any ideal, we have a joint semilattice mapping to 0, 1, which maps the elements of the ideal to 0 and maps the elements not in the ideal to 1. And conversely, given any joint semilattice mapping from a joint semilattice to 0, 1, all right, the set of elements that map to 0 form an ideal. So the characters and the ideals of a joint semilattice are really two ways of talking about the same data. There's an annoying problem here. If we think of we view L hat. L hat is the collection of all characters on L. It inherits the structure of a joint semilattice from 2 to the L. All right, but the mapping from ideals to this object is order reversing. So that's an annoying fact. So what can you do about that? You could, instead of talking about joint semilattices, maybe talk about meet semilattices, or maybe you could just live with it, right? I don't know what's preferable. Now we begin to get to something significant. The lattice, the collection of all, right? Any intersection of ideals is an ideal, and therefore the collection of all ideals of a joint semilattice forms a complete lattice. The function, the function down arrow is a joint semilattice mapping from L to the collection of all ideals. This is not all right. I guess the only thing that is say, I mean, I think it's really interesting how often the fact that some type of set is closed under intersections produces a complete lattice for us. And that's what that lemma is saying. But this is not surprising, pretty well known. More interesting, again, I'm sure that I'm not, this is no news to anybody. We're reviewing stuff that's well known. An element of a complete joined semilattice L is said to be compact if for all subsets of that joined semilattice. If A is less than the sup of X, then A is less than or equal to the sup of a finite subset of X. The compact elements of L are denoted compact L. Now, the proposition tells us that the compact elements of the lattice, the compact ideals are of a joined semilattice are exactly the principal ideals. Moreover, I guess the compact elements of IDL, the compact elements of big IDL of L, the lattice of all ideals of L, the compact elements are themselves a joined semilattice. And down arrow then is a mapping from L to the collection of compact elements of the frame of ideals of L, and it's an isolattice. So this is, all right, you know this, but we're going to put this into a context here that makes it a little bit more interesting in a moment. So this is the second highlight, a second spade in the hand. A lattice A is said to be algebraic if it's complete and every element of A is a joint of compact elements. And famous theorem of, I think it's by Birkhoff, very old, said that for any algebraic lattice. Oh, okay. Before we get to that, let's take a complete joined semilattice, all right, and an element of it. All right, now I'm going to say that eta sub A of little a is the set of all compact elements of A, of big A, which are less than or equal to little a. All right. That is, every compact element of big A produces an ideal in the collection of, let's see, every element of an algebraic lattice, or actually every element of a complete joined semilattice, every element produces an ideal in the collection of all compact elements of that lattice. And the theorem of Birkhoff is that for any algebraic lattice, eta sub A is a mapping from A to the ideals of the joined semilattice of compact elements of A. And it's a bijective function that preserves compact elements and preserves all suprema. So that's an old theorem. It's a characterization of algebraic lattices. And these days we can put it into a category theoretic context. And in the category theoretic context, the down arrow and the eta play the role of natural transformations and provide a equivalence of categories. So we won't check the details, and it does take a little work to check the details, but it doesn't take it. It takes work, but no imagination to check the details here, which I like those things, all right? Because I can always do the work. I don't always have the imagination, but I can always do the work. So the lemma is that IDL is a functor from joined semilattices to category category of algebraic lattices is a category whose objects are algebraic lattices and whose morphisms are the complete compact element preserving morphisms. So IDL is a function from JSA to alg, and compact is a functor from alg to JSL. And these provide an equivalence of categories. You see, to get an equivalence of categories, we need a natural transform from the identity. We need two natural transforms from the identities of the respective categories to the compositions of the functors. And they look like this, and you can verify that it's easy to verify. It takes no imagination to verify that these diagrams commute and give us that equivalence of categories. But we'll leave off the details. Okay. Now, special topic. A very interesting special topic. A joined semilattice morphism is said to be special if it preserves all existing finite infima. Now we're going to let little itl L denote the sublattice of big itl L generated by the compact elements, right? Generated by the principal ideals, if you will. Okay, so we recall, need a new definition here, that a joint semilattice is said to be distributive. A good way to say this is that if every binary cover has an exact refinement, that is, if A sup B is bigger than C, then there's a refinement of A and B, an element A prime less than A, and an element B prime less than B, such that C is exactly equal to prime sup B prime. It's well known that L is distributive as a semilattice if and only if itl L is distributive as a lattice, that is, if and only if itl L is a frame. Now, in 2008, Hansel and Pussart proved this very interesting result. Suppose that L is a distributive joined semilattice, D is a distributive lattice, and phi L to D is a special joined semilattice morphism. That is a morphism that preserves existing infs. Then there's a unique special joined semilattice morphism, phi bar, from itl L to D, such that phi factors through arrow and phi bar. So little itl L has a universal mapping property. And I've always been very fond of universal mapping properties, but that's not why. that's not the reason. It's not just my fondness for universal mapping properties that makes this important. What is the importance of this thing? Hansel and Pussart used this construction to generalize Priestley duality to semilattices, right? The obstacle that they faced lies in the fact that joined semilattices do not in general have enough prime ideals, but itl L supplies them where they are lacking. So recall that an ideal I in L is said to be prime if L not I is a filter. That's what we said earlier. A prime ideal of itl L cuts back to an ideal Q, that is P intersected L, that may fail to be prime, but at least it satisfies the condition that for all finite sets not in Q and all Q in Q, that finite set has a lower bound not in the down set of little q. And that's a weakening of the primality condition. Okay. Now, because we were interested in conjunctive semilattices, it occurred to me that, and because of potential applications that I'll get to in a moment, it occurred to me that it would be interesting to ask whether or not if L is conjunctive, then itl L is also conjunctive, or if what's the relationship between the conjunctivity of L and the conjunctivity of itl L. So let's recall the definition of conjunctive. We say that L is conjunctive if it has a top element, that is, L is a joined semilattice. We say it's conjunctive if it has a top element, and for any pair of elements of L, right, A and B, if B is not less than A, then there is an X in L that sups with A to give something that is strictly less than 1, and sups with B to give 1. That's a first order condition. It's equivalent to condition on ideals. So that's a surprise that it really probably the reason for introducing this definition. L is conjunctive if if it contains a top element, and for any two elements of L, there's a maximal ideal that contains one and does not contain the other. That is, the maximal ideals are sufficient to distinguish points, or that is, the maximal ideals are sufficient to represent the joint semilattice. It is worth mentioning right here that in general, in a conjunctive joint semilattice, the maximal ideals need not be prime. That's a surprising fact. But nonetheless, there's a nice representation theorem based on maximal ideals that we'll talk about in a moment. Now, yesterday, we asked this question is, what's the relationship between the conjunctivity of L and the conjunctivity of idle L? And Drew suggested the following proof. If L is distributive and contains, suppose L is distributive and contains one, if idle L is conjunctive, then so is L. All right, and the proof is worth looking at. Given A and B in L, if B is not less than or equal to A, then there are by assumption elements in L such that down A sup the intersection of the down X's is less than 1, and down B sup the intersection of the X's is equal to 1. By distributivity, we get that an intersection of the A sup X's is strictly less than 1, and the intersection of the B sup X's is equal to 1. All right, well, if the intersection is less than 1, then one of them must be less than 1. But by the second equality, B sup xi is equal to 1 for all I. All right, so we found our separating element in L. And the problem as of yesterday evening is the converse true? And we may have a proof of that. We'll find out today. All right. Let me review the representation theorem for conjunctive joint semilattices, because that's worth thinking about in this context. If L is a conjunctive joint semilattice with at least two elements, then we let max L be the set of maximal ideals of L, and we're going to define a function from L to the power set of the collection of all maximal ideals by sending A to the collection of maximal ideals that don't contain A. That's a joint semilattice injection, and its image is a subbase for a compact T1 topology on max L. And conversely, if X is a non-empty set and T is a compact T1 topology on X, and if L is a subbase for T that is closed under finite unions, then L is a joint semilattice, of course, and it's conjunctive, and the mapping that takes X to the maximal ideal consisting of those elements of L that don't contain X is a homeomorphism of X with its topology with the spectrum of L, the spectrum of the maximal spectrum of L. That is the maximum. That is the set of ideals with in which the cozero sets form a basis for the topology, or form a subbase for the topology. Comment: the maximal ideals of a conjunctive joint semilattice need not be prime, but they are prime if L is distributive. Moreover, if L is distributive, then L is a base, not merely a subbase for the topology. So this is a nice way of looking at what distributivity means, and this is discussed in Gretzer's book, in his chapter on representations of joint semilattices. Yesterday we were talking about, I wanted to include this because yesterday we were talking about a problem of constructing a distributive conjunctive joint semilattice that's not a lattice. And we, this morning, occurred to me that we had a somewhat easier construction than the one that we were thinking about yesterday. Let's let L0 consist of all the subintervals of the real interval 0, 1 form 0A or B1 with A and B and R. All right. Or of the form AB with A and B in Q. And let's let L be the joint semilattice generated by L0, right? Well, of course, then L is a basis for the standard topology on 0, 1. So it's, and I think we can, I don't know, it's a conjunctive joint semilattice, and we can verify that it's distributive. However, if B is less than A, alpha, if beta is less than alpha and alpha irrational, then L doesn't contain a greatest lower bound for 0, greatest lower bound for 0A and B0. The intersection of those two, that is the right. The intersection of those two things is a interval with rational endpoints, but the only intervals which don't have endpoints, which have endpoints in the open interval 0, 1 have rational endpoints. All right, so finally here's the problem that Trussell addressed, and I'm not going to give a lot of detail on this, but the problem was, suppose that L is a distributive joint semilattice with 1. Distributivity here is a necessary hypothesis, and that we have 2 elements in L whose sup is 1. Suppose further that the downsets of each of these sets are conjunctive. Does it follow that A itself is conjunctive? All right, so the downset of A0 is a joint semilattice with top element A0. And the downset of A1 is a semilattice with top element A1. So we're assuming that they are conjunctive. Does it follow that A is conjunctive? All right, Trussell, by a rather difficult and involved argument, which I have still not simplified or fully digested, has proved that the answer to this is affirmative when A is a distributive lattice. So the obvious question, and the thing that motivated me to think about IDL in the first place, was that does little IDL enable us to generalize Trussell's results to all joint semilattices? Or maybe not. find the obstructions to doing so. So that's a problem that fascinates me and has interested me for over a year. I don't know how many hours Chapman Tega and I spent trying to comprehend the meaning of this problem, but it was embarrassing. It's embarrassing to admit how many there were. All right. Now this is a new topic. All right, we're going to change a little direction here and talk about some other interesting results. A topological space Z equipped with a joint semilattice operation that is continuous as a map of the product space Z cross Z to Z is called a topological joint semilattice. Any product of topological joint semilattices endowed with the product topology and component-wise operations is a topological joint semilattice. Each fixed A in Z determines a continuous function, A sup from Z to Z, which sends Z to A sup Z. If U is an open subset of Z, then the inverse image of U under this mapping is a set of all Z's that promote A into U. And of course, it's open for any A in Z. Now, here's a list of some important basic facts about topological joint semilattices. These are listed in the Compendium of Continuous Lattices towards the end of the book, although in a slightly different language. And these are really remarkably powerful results, though they're quite easy to prove. I think the proofs here are included with the statement. If U is open, then the downset of U, which consists of all Z such that for some U in U, U sup Z is in U. That's another way, it's a way of describing the downset. It's open. And the description that is written there shows that it's a union as U varies over U of various open sets. Right. So the theorem is that if U sub Z is open, then down U is open. And the proof is included in the statement. If Z is a T1 space and A is in Z, then down A is closed, since Down A is the inverse image under A sup of the closed set singleton A. And finally, if T is Hausdorff, I think I should say if Z is Hausdorff, there's a misprint there. If Z is Hausdorff and A is in Z, then up A, which is equal to A sup Z, is closed, since A sup is a continuous retraction. And the image of a continuous retraction of a Hausdorff space is closed. So those are some facts that we're going to refer to later. Here's some information about zero-dimensional topological joint semilattices. The category of zero-dimensional topological joint semilattices is denoted ZJSL. The subcategory of compact or locally compact objects is called CZJSL or LCZJSL. Right. The two-element joint semilattice with a discrete topology is a compact zero-dimensional joint semilattice. Thus, for any set X, 2 to the X with the product topology and the component-wise operations is a compact zero-dimensional joint semilattice. Maybe this should have been in gray, but we can stop for a moment and think about this. The basic open sets of 2 to the X are specified by fixing finitely many coordinates, and these are Clopin. Indeed, requiring 0 at all the coordinates in a finite subset A of X creates a Clopin downset called D sub A. Yeah, that's a technical fact, so we don't need to think about it too much, but it results in that kind of a nice description of the Clopin downsets, which comes in handy in proving things, but I won't concentrate on this. Let's review here. JSL is the category of joint semilattices and zero sup preserving maps. CZJSL, compact zero-dimensional topological joint semilattices, continuous joint semilattice maps. The locally compact version is here. Now, the duality theorem for semilattices traces back to a paper of Austin, about whom I know nothing, other than that he wrote this paper in 1963. And Austin was credited with being the first to discuss this duality theorem by Hoffman, Mislev, and Stralka. And these folks wrote a whole Springer lecture notes on it in 1974. The duality theorem reads as follows. The Hom functors, right, JSL, that is the joint semilattice mappings to 2, they form a compact collection of all, right? If JSL L to 2 happens to be, or it can be thought of as a subjoint semilattice of 2 of a power of 2. It can be shown that it's closed subset in a power of 2 with the product topology. All right, so JSL, the Hom functor to 2 gives us a functor from JSL to compact zero-dimensional joint semilattices. And conversely, the continuous characters on a compact zero-dimensional joint semilattice form a joint semilattice. And the duality theorem says that these functors provide a dual equivalence of categories. All right. So there was a little bit of comment down below about the functor. I said suitably enriched, right? JSL L2 inherits a compact zero-dimensional joint semilattice structure from 2 to the L. And the CZJSL inherits a joint semilattice structure from 2 to the Z. I'm going to denote the enriched structures by hats in imitation of what happens in Pontryagin duality. Okay, so some background on this. To prove this duality, we need to show that if L is discrete, or respectively compact zero-dimensional, then L hat is compact zero-dimensional, respectively discrete. And in both cases, we need to show that L is naturally isomorphic with L hat hat. All right, so there's lots of ways to do this, but it turns out that the real part, the difficult technical step is to prove that there's enough continuous characters on a compact zero-dimensional joint semilattice. Okay. So Hoffman, Mislov, and Stralka obtained this as a corollary of something of a lemma of Numakura. Numakura proved that every compact zero-dimensional joint semilattice is a projective limit of finite semilattices. Okay. Well, finding the relationship between compact zero-dimensional joint semilattices and finite joint semilattices is the key to much of this. And it's the key to much more general collection of duality theorems that are described in Johnstone, his book on stone spaces. So the book is on, that chapter is titled Ind and Pro Objects. And there's a general categorical machine in there that will produce lots and lots of dualities from finite dualities. So they maybe one of the more efficient ways of getting, well, an efficient way of proving HMS duality is by means of Johnstone's machinery, but nonetheless, you still need to prove something along the lines of what's written in blue here, that there are sufficiently many characters. Okay, so we're going to see how to prove this by a lemma that Jimmy Lawson suggested in last August, just a year ago. And it's remarkable that it works not just for compact zero-dimensional joint semilattices, but for locally compact zero-dimensional joint semilattices. And the fact that it works with this generality really makes one wonder whether or not there's a generalization of HMS duality to the locally compact case. And the fact that Pontryagin duality does have such a generalization, all right, is additional enticement. But of course, all right, there's a lot of subtleties involved. So it's by no means clear that there is a generalization. I should say that right here. Lawson's lemma has such a beautiful proof that I want to go through that, and it won't take very long to do it. So we're going to suppose that Z is a locally compact zero-dimensional joint semilattice, and W is an open down set. And what we're going to show then is that W is the union of all Clopin principal downsets that it contains. So to prove this, we need to for each W, and then the result that we need is going to be an easy corollary of this. For each W and W, we're going to find a Clopin principal ideal containing little w and contained in big W. Step one. By the hypothesis of local compactness and zero dimensionality, we can find a Clopin set V such that W is in V and V is contained in big W. Now, construct a maximal chain, ascending chain, starting at little w and contained in big V. By the third fact, all right, by the third top fact that we mentioned earlier, the sets up W, up X, up Y, the upsets of the elements of that chain form a nested family of closed sets, right? Top fact 3 says those upsets are closed sets, each having non-empty intersection with V. But by the compactness of V, there is at least one point of V in all these upsets. And by maximality of the chain, there is only one such point. So we're going to call that Z sub W. Okay. By continuity of the joint operation, we can find a V prime containing Z sub W and contained in V, such that that is closed under the sup operation. And then this makes Z sub W the largest element of V prime. And since for any V in V prime, V sup ZW is in V prime, and by maximality of the chain, this element cannot be strictly greater than ZW. That is, right? All right. So Z sub W is the largest element of V prime. It follows from top fact 1 and top fact 2 that down ZW is equal to down V prime, and this is a Clopin ideal. So it contains W, since W is less than ZW, and it's contained in W by construction. And this is why Jimmy Lawson is known as a smart guy. So here's some corollaries of Lawson's lemma. The continuous characters of a locally compact joined semilattice separate its elements. Or suppose that Z is a locally compact joined semilattice. A and B are in Z, and A is not less than B. By top fact 3, the complement of A up is an open down set. By hypothesis, it contains B, and hence by the theorem, B is contained in a Clopin down set that does not meet the upset of A. Another corollary, suppose Z is a compact zero-dimensional joined semilattice. Define Z to phi sub Z to be the mapping from Z to the set of characters on Z hat, where we define big phi sub Z of chi to be chi of Z. Then big phi is a equivalence in the category of compact zero-dimensional joint semilattices onto its image. Phi is continuous, and by Lawson's lemma, it's an injection. Since the codomain is Hausdorff and the domain is compact, W is a homeomorphism onto its image. So here are some questions that remain open that refer to the possibility of extending the duality. Suppose Z is a locally compact joint semilattice. Is Z equivalent as a topological joint semilattice to a subjoint semilattice of 2 to the power Z hat? I don't know. The map phi that we described above is a continuous injection. So to answer the question in the affirmative, it would suffice to show that phi is an open map. And to do this, it would suffice to show that the principal Clopin ideals and their complements form a subbasis for the topology of Z. Well, I don't know if that's the case. So there's something to work on. So we've covered 23 slides and 55 or 50 minutes. The only thing left over is this. All right, 23 chromosomes. 3 of them are X's. We must be in the Barbie movie. All right. I don't know. That was just there as an extra slide. Oh, well, that's what I wanted to talk about. What I will do is put these slides in Google Docs, or we can email these slides. I'll email these slides to Tega, and she can mail them out to anybody, to you all. All right. How about that?
Thank you.
Yeah.
Time for questions.
Yeah. Questions?
In the definition of conjunctive, you need top element, but is
Yes.
it possible to have some version of this?
Yes. Yes. It's discussed at length in the paper with Tega and Chip. Yeah, the possibilities there are that's something that we explored and that we had lots of questions about. I don't think we know much definitively about it.
There are some historical things, that I
Well-
can either email to you or I can mention now, but there are some historical things that you didn't mention, so.
Which things?
For example, you give credit to Birkhoff for this classic result, but I think that Nachman is one of the guys who deserves also credit.
Okay.
I think Nakpin was probably the first, as far as I know. I'm not sure, but it was all happening in the 40s, so.
Yeah.
Nakpin has a,
Yeah,
Uh-huh.
I didn't, as people asked me, what was the origin of these during the lecture? I didn't intend to be, right, I put in some references, but I didn't intend them to indicate priority.
Yeah, but that semi-lattices and algebraic lattices go hand in hand. That's probably Nakpin, and before Birkhoff,
Okay, yeah,
And then you give credit to Hansu, for that lemma, but it also goes back to the 70s, So I discovered that recently, it's really Cornish in 1978 who proved that.
who?
Cornish.
Cornish, oh, okay.
Yeah, and I can email you the paper if you're interested,
Oh, I'd
and,
love to get it, yeah, I'd love to see that, yeah.
yeah, I actually have
Yeah.
the paper, and also, this Hansu duality that you're talking about, Priestley style, there are some other people who've done work on that, I can
Including you, I
myself.
believe.
Huh?
Including you, I think.
Including myself, yeah.
archive
So
paper on
I can email you some papers on that too,
Yeah, please do. Yeah, go ahead and email me everything that you got. Yeah.
And then one question to finish it off, so when you talk about this generalization you're interested in, so this classic result, what they call this Pontryagin duality for semilattices, states that these semilattices are dual to the stone semilattices. Now, this locally compact generalization you want, how do you want the result to be? What would be the generalization that you are after? How would you phrase it?
Some category of, all right, some category of locally compact joint semilattices should be self-dual. Maybe that would be nice. Something like, I mean, Pontryagin duality, starts off as a duality between discrete groups and compact groups. And then it generalizes to a duality between locally compact groups and locally compact groups. And the lemma, or the fact that's needed to create that result springs from sort of some kind of uniformity condition that arises because you've got the group action. So with the case of joint semilattices, I don't know that there's anything similar. So it may be that it's just pie in the sky to even believe that there's a generalization.
And
Because
did you look in Johnstone's book? He has some semi-duality results in the last chapter. I mean, how do they, whether you looked at them and how do they relate, to what
yeah,
you're
I'll
at?
have to, I didn't look at them, so I'll have to look at them. Yeah.
'Cause he has some semi-duality results there,
Right, there's a bunch of stuff about locally compact
Yeah.
groups in that last chapter, and the last chapter is one thing, that book that I never went to bed with.
Okay. Thank you.
Oh, you're welcome. I hope it was entertaining.
Yeah. This is the stuff that I know a little bit about, so I'll send you an email,
Wonderful, yeah. Well, I think you know a little bit more than you know more than a little bit.
Just a little bit.
Yeah.
I had a question about this paper by Austin. I don't think I know it. It doesn't have the duality in it.
If it does, it's hard to see it. But Hoffman, Mislov, and Stralka acknowledge it and say that they see a embryonic, or they see the embryo of their result in that paper, or they see a manifestation of their result in that paper.
But to call it the Hoffman Strelka duality is not a misnomer.
No, Austin proved some kind of a duality. theory, but it didn't look exactly like what Hoffman and others showed. Here we go. Hey, Rick. How are you?
Well, thanks. Nice talk, Jim. Thank you.
Oh, you're welcome. I thought I would find you in the math lounge at Chapman.
Oh,
Why don't you show everybody?
You're not showing Drew. No. Drew is not showing.
Oh, Drew is not sure. There's, oh, oh, there he is. There he is. There he is. All right. Well, it's lunchtime.
thanks again.
Good seeing y'all. Look forward to seeing you again as soon as possible.
Thanks, Jim.
Bye-bye.
Thank you. Thanks, Jim.